So yeah, hello everyone. Today I'm going to discuss this expanding horizon 6.0 coding test. Without wasting much time, let's get started with the problem one. Okay, so the problem uh, one was Aditya and vintage treasure map, right? So let's read this problem now. Aditya, a passionate historian, has discovered the ancient vintage treasure map. Okay, so this part was just a storyline. Now let's see. Basically, Aditya must plan a single uninterrupted expedition along the route to recover the maximum possible wealth. He believes, okay, he believes that unlocking the treasure. Okay, so basically, sorry, the question says that we are having an array like this, yeah, which will be having some integers. Okay, so the maximum wealth is basically the maximum subarray sum. Okay, and the integer values can go up to positive and negative 1e9. And the constraint for n is 1e5. Okay, let's see this problem now. Let's quickly see the sample test case first. This was the sample test case, right? Let me take a snap of this. What? So this was the sample test case, right? Let's quickly see this. So in this array, we are having integer minus 2, 1, 3, or minus 3, 4, minus 1, 2, 1, and minus 1, right? Okay, it has been resumed. Yeah. So basically, we are having this array. Let's consider this array now. Minus 2, 1, minus 3, 4, minus 1, 2, 1, and minus 1. Let's consider all the possible subarrays, right? Okay, so increase the subarray sum. Basically, as we all know, to find the maximum subarray sum, there exists a algorithm which we call as Cadane's algorithm. This problem was just a simulation of that algorithm only. Let's quickly see the pseudocode, or you can say the algo part of that Cadane's algo. So Cadane's algo. In Cadane's algorithm, we generally have an array. Let's say we are having indexing from 0 to n minus 1. This algorithm, we store two particular sums, the current sum and the max subarray sum. Right. Let's initialize the current sum with 0 and the max sum with negative infinity, or you can say minus 1e17, because the negative elements are also there in the problem. Okay, so let's quickly see its pseudocode. So let's iterate through this array. Int I goes from 0 to n minus 1. Okay, while iterating, let's increment the current sum with the array value. Okay, and whenever I have updated the current value, this current sum, let's update the max subarray sum as max of max sum and the current sum, right? But there is a catch. Whenever my current sum becomes less than zero, basically whenever my current sum becomes negative, I have to uh, basically shift the sub-array part so that the next sub-array sum should start from zero, right? Because I need to maximize the sub-array sum. So that's why whenever it gets negative, I have to update it with zero. So whenever the current sum becomes negative, let's update the current sum as zero. Okay, and run this cycle. After this loop, I will be having my maximum current sum, my maximum sub-array sum. Let's try to dry run this. Okay, you are having this array, right? Wait a second. Copy the array. Yeah. In this array, yeah. So right now I'm having my this array, right? Let's try to. So initially I equals to zero, right? So the current value, the current sum is equals to minus two. So I got negative sum. Let's update this with the zero. Uh, Before updating, sorry, I have to update the max sum also. So when I got current sum as minus 2, the max sum I have updated with minus 2, right? Yeah. So after this step, my current sum was negative, so I have to update this with 0. Now quickly update the I value. So I has become first index 1. So now the current sum will become 1. As it is positive, there is no need to update this thing. Maximum sum is updated by 1, right? Again, I will, it's right, I equals to 2, right? Now the current sum will become 1 minus 3, that is minus 2. So maximum sum is max of 1 and minus 2, that is 1 only. So as it is negative, I have to update this thing with 0. After that, let's shift the index. So index is I equals to 0, 1, 2, 3. Let's update the current sum. This is 4. Maximum value will get updated. It will become 4. Let's now go to index equals to I equals to 4. So the current sum will become 3. Max sum is will still remain 4. Then I will go for I equals to 5. Current sum will become 5. Max sum will become 5. I will go for I equals to 6. Current sum will become 6. Yeah. And max sum will again become 6. For the next step, the current sum will become for I equals to 7. The current sum will become 6 minus 5, that is 1, and max sum will still remain same, 6. So let's quickly see the output for this test case. Minus 2, 1, minus 3, 4, minus 1, 2, 1, minus 5. Right. So this was the array. And what I have seen is when I was at this end and I got the maximum value, that is 6. So this sum was from this part. So this was the subarray which was giving me the maximum subarray sum. So let's quickly analyze its time and space complexity for this Cadine's algorithm. So for Cadine's algo, I haven't used any extra space. So the space complexity will be constant apart from the input array. Let's quickly see its time complexity now. Its time complexity should be linear because I have iterated the array single only one time. Okay, so let's quickly code this solution now. Yeah, the input format for the problem. So input format was first time I'm having my n. Okay, this is just my template. Taken n as input. Then I have to take a array as input. Okay, let's initialize. VLLS is just vector of long. ARR. This is yeah. REP is by loop. I can use this also. I goes from 0 to n. I plus plus. Let's take input. I write. So after this step, I have to write algo for cadence. Right. Let's initialize the current sum as 0 and max sum as minus 1 is 17. Right. So let's iterate through the array now. Current sum plus equals to of I and max sum, not max element, equals to max of max sum comma current sum. And if the current sum becomes less than 0, then I just have to update the current sum as 0. After this loop, I just have to output the max sum. Yeah, okay. Let's take sample input. 8 minus 2, 1 minus 3, 4 minus 1, 2, 1 and minus 5. Output should be 6. Let's see. Runs or not. Is there any error? Okay. So I have to make it current. So what? Yeah, it was not max sum, it was mx sum. Let's now run it. The output is 6. Let's now submit this code. C++. Let's see whether all the test cases are passing or not. Okay, all the test cases have passed. Now let me. Okay, so let's quickly summarize this problem again. Basically, the this part was just the storyline. Then in this part, Aditya sir has just explained us that he need the maximum subarray sum of any subarray, and the constraint for the problem was n is going from 1 to 1e5, right? Whereas the elements are from minus 1e9 to 1e9. This was the range, and we need to find the maximum subarray sum for this particular array. And we all know that for maximum subarray sum we have a algo known as cadence algorithm, in which we just initialize our current sum and maximum sum, current sum with 0, maximum sum with negative infinity value, and then just iterate the array only one time, update the current sum by adding the current index value, update the max sum, and if the current sum becomes negative, we have to shift the subarray and update the current sum of that subarray equals to 0. And after that, just return the max sum. This was just dry run part, and the space and time complexity for this cadence algorithm was Space complexity was big O of 1 and time complexity was big O of n. Okay, so so let's quickly start the problem 2 of the quantity test. So the problem 2 was Sahil and his delusion, right? So let's quickly read this problem. Is saying, yeah. So Sahil and Supreet are two players in the retro arcade tournament navigating through the tower of pixels. Okay, and that tower has n levels. Okay, numbered from 0 to n minus 1. Okay, each level is guarded by the pixelated boss. Okay, with specific strength. Nice. Represented by an array of strengths. Here, strength of I represents the strength of ith level boss. Okay, nice. So this was the problem. Let's quickly read the rules. If a player is currently on ith level, okay, they can advance to jth level only if the boss on the jth level has higher strength than boss on the ith level. Okay, and jth level is above ith level. Okay, and jth level is closest to the ith level. Okay, let's try to quickly visualize this thing. Basically, the problem is saying that we are having a tower, something like this, and for this tower, we are having multiple levels, level 0, level 1, level 2, goes on up to level n, right? And at each level, there are some bosses are present at each level, right? And these bosses are having some kind of strength, which is represented by strength of I, right? So, let's try to understand the rules. These rules are saying that if this was the tower and a person, if a person is currently at this particular level, let's say ith level, then he can go to jth level if and only if this particular jth level, for this particular movement, the three of these conditions should match. Yeah. What are these conditions? The first condition is strength of j should be greater than strength of I. Okay. J should be greater than I and j should be closest to I. What does that mean? Let's try to visualize this thing. Okay, let's take an example of some kind of array. Let's say we are having an array, something like this. Let's say ARR. We are having two indexes, I and J. You can visualize this movement from I to J if and only if this J is greater than I, array value of J is greater than array value of I, and J is closest, right? If you all are aware of a standard problem known as how to find the next greater element in an array, so let's quickly see what next greater element is. NGE, that is next in an array. Right? Sorry, yes, there was some lag. I was saying that if I am having this particular array, so for movement of this type, I to J, uh, there should have it should have it should be yeah. For movement from I to J, these three conditions should hold. That is, J should be greater than I, array of J should be greater than array of I, and J should be closest to I. And I was saying that there exists a standard problem known as next greater element, whose conditions are exactly same to these conditions. Okay, so let's see what is the next greater element in an array. Yeah. So next greater element states that uh, jth element is next greater of ith element if j is greater than I and it is the first right side of I, which is greater than ith index value. Right. So as we all know that to find the next greater element in an array for each index, we can use a stack. Right. Let's see how we can use this concept with respect to this problem. Right. Okay. So this was the condition for this travel part. Let's now understand the second part of the problem. So after this rules part, let's understand the task which we have to perform in this problem. So the task is we have to answer Q queries for each test case. Basically, yeah, we are having T test cases, and for each test cases, we have to answer Q queries, right? And in each query, we need to answer. Yeah, in each query, we are having two coordinates, or you can say two levels, level X and level Y. X states, yeah, X is the starting level of Sahil, whereas Y is the starting level of Supreet. And we need to find whether Sahil can reach to Supreet's level or not, if Supreet is still, right? So this is the task. And constraints for this problem are test cases are up to 100 and in Q are up to 105, right? And strength can go up to 10 to 19, right? Let's quickly understand what problem is saying. The problem is saying that we are given an array. Why it is not syncing? Yeah, we have given an array in which for each index 0, 1, 2, 3 goes on up to n minus 1. We have, let's say, yeah, we have this ith index value as strength of I, right? And we need to answer Q queries for each test case of this type x comma y, and we need to answer whether the guy Sahil standing at x can reach y or not, right? Based on that, I need to answer as yes or no. Yes, this is the problem. Okay, let's try to understand through a sample test. Yeah, four. So the array was 4, 1, 6, 3, 5, 2, 7, 8. Right? And the queries are 1 to 7, 2 to 5, and 1 to 2. Right? Yeah. So these are the queries, right? Okay. Let's try the first query. So the first query is saying that let's do some kind of indexing first. 0, 1, 2, 3, 4, 5, 6, 7. We have just understood that a person standing at ith index can only go to the next greater element of its of that index. if there doesn't if the next data element of that index doesn't exist, then that person is stuck at that index, right? This was clearly mentioned in this third rule. Not third rule, yeah. Here, if no such j exists for level I, the player will get stuck on the ith level, right? Okay. So let's try the first query. So the first person X is standing here and Y, the person Y is standing here, right? Let's try to simulate the process. Okay, so person standing at this point can go only up to this point because for the index 1, value is 1, so its next data element is 6, which is at second index. So now currently if it is standing here, he can only go to this index because for 6 the next data element is 7 whose index is 6. Now yeah, after 7 he can only go up to this last index whose value is 8. So the path is started from first index, then he reached second index, then he reached sixth index, and then he reached last index 7, which was the required index. So for this particular query, the answer should be yes. Let's try to simulate the second query. 2 to 5, right? So initially the person was standing at this point, right? Let's see. From second index, the value is 6, so the next data element is 7, which is present at the sixth index. So from 2, he can only go up to this sixth index, and then from 6, he can only go up to 7. So in this whole path, that is from 2 to 6 to 7, we Sahil can never reach the index 5, right? So for this query, he can't reach Supreet, so the answer should be no. Let's see the third query. Third query was 1 to 2. As we have sorry, as we have already seen in the first query that from 1 he can go to 2. So the output for third query should be yes. But let's see the brute force solution for this problem. Let's say we have calculated next data element. Okay. We have already calculated the next data element for each, right? Let's try brute force solution now for this problem. There's some lag in the video. Some internet issue. In brute force solution, what I will do is uh, initially I will evaluate the next data element for each index. Then second step, I have to process for each query, right? So for auto xy belongs to query of I, not queries. Yeah, I need to iterate for the path from x to y, and then I have to check whether that y exists in that path or not, right? So let's say the current element is x, while the current element is, yeah. So I was saying that I have initialized the current by x, and while the current value is less than n, right? Let's iterate the for a current value. I have to change my current value as yeah. current is equals to NGE of current, and if here I have to check for that part. Uh, yeah, if my current value by any chance became y, then I need to return for yes. Otherwise, I just have to iterate this step. And if the loop this while loop has completed and we haven't returned anything, that means we have to return no. Right? Let's try to analyze its time complexity and space complexity. As we all know, that NG part will be big of in space and time complexity both using stack, right? So overall time complexity will be big of test cases multiplied by query, and for each query I am iterating from this x to y. In worst case, this can be n, right? Let's see. Test cases are 100, queries are 1e5, and this n is also 1e5. So definitely this will give me TLE because this is 10 to the power 12. So that means I can't write the brute force solution. Let's try to optimize this thing, right? Okay. Okay, yeah. Let's see if we can optimize this step, because in for each query iterating from x to y is somewhat, you can say, a wastage of time, right? So let's try to optimize this thing. How to optimize this thing? uh, let's say if I can store all those indexes for each index I, where person standing at I can go, and if I can access that or check that thing some time complexity less than big of n, complexity will be, let's say, big of t uh, 2 into, let's say I am using log n, if let's see if it is possible. So 100 1e5 log of 1e5, log of 1e5 will be less than 20. Let's see. It will be something like 18 or 19, I guess. Let's take it as 19. So 1.9 into 10 to the power 8 in worst case scenario. So this solution should work. Let's try if we can store, like if we can store all this information. Okay, for this, uh, let's say I am storing this information inside a vector of set of it. Say I'm taking long, right? Let's call it as V, which is storing basically V of I is storing a set of all indexes S's where person standing at I can go, right? We all know that we can check whether this particular y index is there in v of I or not just by using the find function, right? V of I dot find I. We know that the time complexity for this should be log of n in worst case scenario, right? Let's try to build this. Okay, so let's say let's take a sample array. This array, let's say. Uh, let's say the array was 4, 1, 6, 3, 5, 2, 7, 8. Right? This was the array. Let's do some indexing. 0, 1, 2, 3, 4, 5, 6, 7. So this was the array. And say I have already evaluated the next data element using the stack. Let's see the NGE array for this particular array. 3, 6, 7. 0, 1, 2, 3, 4, 5, 6, 7, indexing. Okay, so for 4, the next data element is 6 and its index should be, and its index is 2. For 1, the next data element is 6, so index will be again 2. For 6, the next data element is 7, so the index will be 6. For 3, the next data element is 5, the index will be 4. For 5, the next data element is 7, and the index should be 6. For 2, the next data element is 7 and its index is 6. So for 7, the next data element is 8, its index is 7. And for 7, there is no next data element, so I'll be having -1 for this, right? Yeah. Let's try to build a V of I. Let's say I am iterating from right to left to build the V array. Okay. Let's say I am currently at this index 7, right? So uh, from particular index, I can reach how many indexes? Like all the indexes in that path from, like let's say I have index x, then I will go at next data element of x, then next data element of that, then that, and so on. Okay, so first quickly push, like v of n minus 1 should have n minus 1 first of all, definitely, and only this element. Let's see when I am at this index, right? Okay, so we all know that from 6, the for this index 6, the next greater element is 7th index, right? That means from 6 we can go to 7. That means that uh, first of all, v of n minus 1 should, from that index I can go to 7. Basically from 6 index I can go to 7, and from 7 index I can go to all these v of n minus 1 indexes, right? That means I can append this particular set to the set of v of n minus 2, right? So let's see. First of all, I have just said that v of n minus 2 is equals to v of n minus 1, that is equals to n minus 1 index, and also I can go to this current index also. That means from n minus 2th index, that is the 6th index, I can go to 6th index and 7th index, right? This is just 7th index. this was 7, right? Yeah. Let's see for this fifth index, V of 5. As we all know that the next great element for 5 was sixth index. Okay. So build this thing. Yeah. Which was 6 and 7. And also from fifth index, I can go to fifth index also. So fifth, I can build this set, right? Yes. And for uh, V of 4, let's see, the next data element for the 4 was again sixth index. So let's initialize this with V of 6, which was 6 and 7. And for fourth index, I can also go to fourth index. So 4, 6, and 7, right? Yeah. And then uh, let's calculate the V of 3. For 3, the next data element is fourth index. That means I can go to 4, 6, 7, and also I can reach to 3 also. So 3, 4, 6, 7. In similar manner, I can build the V of 2, V of 1, and V of 0, right? After that, let's see the overall algo for this particular solution. What I will do is optimal solution. So the first step is evaluate next greater element for each index, right? And after that, uh, we have to process each query. And before processing query, I need to build V array, that is vector of set, right? By just doing this thing, uh, I goes from last index, first index. First of all, if I plus 1 is less than n, then just v of I is equals to, not this, sorry, uh, if the next greater element of that index exists, if it is not equals to minus 1, then v of I is equals to v of next greater element of that index, right? And also, v of I should have the current index also, I, right? So after this step, I'm having my v array with me. So after this step, I'm good to process all the queries, right? So for it goes from 0 to 2 minus 1, right? For each query, I'm having my x. X is my query of I. Let's see if I am storing this x and y. Let's take I also. Okay, first of all, if this y is less than x, that means I can never reach to level y from x, because we all know that we can travel to right side only, right? That means I should just return. Otherwise, I can check if v of x dot find y is not equals to v of x dot end. That is that this y index is there in that set or not. If it is there, return yes. Yes, return no. That's all about this problem. Let's quickly analyze its time and space complexity now. So, uh, building ng is just big of n. Then building the v array is big of n log n. And then processing all queries is just big of q log n. So the overall time complexity is n log n plus q log n, right? And space complexity is big of n for that stack and extra array. Let's quickly code the solution now. I guess there is some lag. Let me check my. Yeah, I am audible, right? Yeah. So I have discussed the time complexity and the space complexity of this optimal approach. Let's quickly see its code now. Code. Okay. Okay. Yeah. So Sahil and Delusion, right? So initially I have taken the n and q as input. Then I have initialized the strengths array. And then uh, PLL is just pair. I have stored the queries of form x comma y inside this queries array. Sorry. Then I have taken the input. I have taken strengths array as input. Then this is next data element, and by using stack, I have built the next data element, and I have stored the next data element's index, not the value. Okay. Then, as I have discussed, I have created a vector of set in which basically v of I stores all those indices where a person standing at ith level can go, right? And have built in reverse manner. I going from n minus 1 to 0. If next data element of that ith index is not equal to minus 1, then I have I have appended the next greater element. Yeah, I have appended all those indices where I can reach from next greater element of that index. Then I have inserted ith index also, because if I am at ith index, that means I can reach to ith index as well from that index. Then I have just handled all the queries. I have taken input, then I have stored x and y inside my query vector. And as I have discussed, if x is greater than y, that means I reach yth level because I can go to right side only, right? Otherwise, I have just checked whether this y exists in the set of all those indices from set of all those indices which I can reach from x index, right? If this is the case, then I have returned yes. Otherwise, I have returned no. Let's quickly run this code. Okay, let's take the input. One test case, 8 and 3 as n and q. Then I have taken strength array 4, 1, 6, 3, 5. Okay, 5, 2, 7, 8. 2, 7, 8. Then the queries 1 to 7, 2 to 5, and 1 to 2. It should return me yes, no, yes, right? Let's see. I have filed the code. Okay, it's taking some time. Yeah, output is yes, no, yes. Let's quickly submit this code now. Let's see whether all the test cases have passed or not. Yeah, it got accepted. 80 on 80 score. Before going to next problem, let's quickly summarize this problem again. Basically, the problem was, uh, yeah, I'm having a strength array. Okay, and I have to answer q queries for each test case of type x comma y, and I need to answer yes or no based on that key, whether I can go from x level to yth level or not, right? And to move from one level I to j, the rule is j should be greater than I, and strength of j should be greater than strength of I, and uh, j should be as closest to I. Basically, from a particular index, I can only go to its next greater element. And if its next greater element doesn't exist, that means I can't go to any index or any level from this particular level. Okay, this was the problem. So as we have discussed, we have to find in brute force solution, we have evaluated the next greater element, and then I have processed all the queries by simply iterating all the paths from uh, x, and I have checked if y is there in the path, then I have returned yes, otherwise no. But this solution was of time complexity t cross n cross q, which was up to 10 to the power 12. So to avoid TLE, I have recomputed this step using vector offset. And using vector offset, I have stored set of all indices where a person standing at I can go, right? And I have built that array, that vector offset in that this manner. I am going from last index to the first index, and if the next greater element of that index doesn't exist, if it exists, sorry, I have appended the set to v of I, and then I have also inserted the ith index to that set. And then I have just answered these queries of type x comma y. Overall time complexity of this new code is big of n log n plus q log n, which is not problematic. One more thing before going to next problem, let me discuss another optimal approach. One more optimal approach that can be that by which we can solve this problem also is use of segment trees. Okay, you can observe that there is a slight pattern in this problem. We can go from x level to yth level if and only if, like, let's let's imagine that thing, x to next greater element of x, which will definitely be greater than x, that is next greater element of x. Then from that element I can go up to next greater element of that index, that is next greater element of x, right? And so on. So basically, if this is the path that from this index I'm going to then this, and then finally, let's say I'm reaching y. Okay, so this was x and this was y. So this can only happen if and only if that all these intermediate nodes, or you can say the intermediate levels, are having the strength value less than y. If the maximum of this particular interval is greater than y, then the output would be no. So by using this particular scenario or use this particular observation, we can use segment trees to answer this problem. So I'm not going into that much depth for segment tree solution because I don't think that segment tree is required for you to learn before internship, right? But still, let me quickly discuss the segment tree solution. So this was the basic input stuff, which is similar to the previous code. I have taken n and q, I have taken strengths, queries, and after taking strength array, I have built the segment tree over this strength array. I have initialized this and built this segment tree over the strength array, and I have just evaluated for each query whether the maximum value in this range, xth index, basically this is max value of strength in interval not x, x2, y minus 1. Because upper bound is up to y minus 1 in my segment tree template. And if this maximum value is greater or equal to the strength of y, then I have to just return no, otherwise yes. Right? Let's quickly see my segment tree template. So I have used struct. I've taken this size and vals vector, and in initialization step, just I have this is uh, standard segment tree initialization where I have just initialized my size by 1 and made it a power of 2, then initialized all the values uh, minus infinity. Then I have implemented this build function in which at the leaf level I have uh, my vals of x as a of lx. I'm not going into the depth of, I'm not going into basically the implementation part of the segment tree because this is not that much required for you. But still, if you know how to write segment tree, then you can practice the segment tree solution as well. This is just simple set function of segment tree, and this is just the maximum of interval. That's all for this problem. For this, the time complexity will be big O. Overall should be n plus q log n. Yeah, extra log n factor is removed. So let's quickly submit this code now. Let's see whether it runs or not. Yeah, it is getting accepted. Yeah, let me tell you one thing. Many of you are trying, have tried this problem using segment tree, but got TLE. Many of you got TLE because you are trying to use this build function. It is, yeah, this build function, and you have passed this array using pass by value. You haven't used that ampersand over here because if you use pass by value in this case, you are trying to segment tree for each test case, right? Not for each test case, uh, for each query, I guess. Wait, let me check this. Sorry, yeah. You are trying to build segment tree for each test case, and for each case, you are using pass by value instead of pass by reference. That's why that copying stuff was giving you TLE. And apart from this, you were not using fast input output, and also you were using backslash. You were using endl instead of backslash n. That was yeah, and these stuff were giving you TLE because there are a lot of queries and test cases in this problem. So fast input output is one thing that can resolve the TLE part. That's all for this problem. I'm breaking this solution part in solution video in two parts. So that's all for the first part in which I have discussed problem 1 and problem 2. Okay, so see you all in next video, and for that, bye bye.